and today we're going to make together the assignment number 4, which is subdividing a surface, extruding the subdivision polylines, and using a tractor curve in order to manipulate the opening and the extrusion level of every um, extruded subdivisions on the surface. So in the end, we're going to end up with something like this that you can see. For example, there's a curve that is the attractor, and based on the distance that it has to our surface, it will create um, this effect that distributes different extrusion length along these modules, as you can see. Also, it affects at the same time the amount of opening, the openness of these modules. We're going to go step by step to see how we can create this object in Grasshopper. So first off, I'm going to make one surface in Rhino, and preferably something a little freeform. Therefore, I'll rebuild the surface into 6 by 6 control points. The degree 3 is fine, so I'll rebuild it. And then I'm going to use control points, preview them on, so that I can create my freeform surface in Rhino. Let's say this is what I want. And now I want to assign it into Grasshopper. So I'll just type surface. And I would assign the surface from Rhino. Then I can just hide it in Rhino. So the first thing I want to do here is subdividing my surface. So in order to do that, we go to domains, divide domain 2D, and then I can assign my surface as an input to the domain. So it already reads what is the surface, U and V, and it creates a domain from them. And then I can subdivide it based on the V and the U and the V counts that I want, that I wish my surface to be subdivided by. So for example, I can just say, well, if I want it to be looking a bit more like equal subdivision, then you see how stretched, what is the shape of my surface? How stretched is it in one direction? This one looks pretty much like a square, so I can just use like the same numbers here. For example, 15 and 15 for each of these U and V subdivisions. The next step is to use isotrim. Isotrim is the component that we use to subdivide surfaces. Isotrim, yes, this one. So again, initial input surface, and then here the subdivided segments could be the ones that we use as an input for the domains. So if you look at it, then you see like there's subdivided surfaces already projected on the surface. So I can preview off the base surface, and here the output should be 225 untrimmed surfaces. So if I already want to check that they are separated or not, here I can just grab a list item, and then this is the item 0 in the list of surfaces. And you know, I can pretty much select each of them that I want. So here is our subdivided surfaces, and then the next step is to extract the edges of them and make polylines, and those polylines will be the base polyline that later we want to extrude. So for that, I have to just type brep deconstruct brep. Sorry, this is the component that you can explode, meaning that you extract information such as face, edges, and vertices, the points, from one surface or a poly surface or any brep basically in Grasshopper. And if I already connect surface to brep input here, it immediately explodes the surface. So it gives me like a list of 225 surfaces and the same number of lists, but in this time 4 edges included in every branch of data, and the same also for the vertices, because there are like 4 points on every surface, right? And now we want to just extract the edges and rejoin them into closed polylines. So if I just type join curves, it should be connecting the edges to the curves. And it is very important that we actually keep the same data structure. We don't want to go flattening it or grafting it, because we want to make sure that every branch of data that includes 4 edges would join those 4 edges within the same data structure. So if you do this, and now I want to just check the output with a panel, then I end up with having the same number of closed curves, which are the edges. So these are the polylines that I want to work with. The rest I can just preview off. So what is the next step? If I want to actually make a loft between these polylines and the offsetted polylines, which are actually what we call it extrusion, is basically we want to offset them based on their normal direction, the normal directions of these surfaces. So first we have to find out each of these surfaces center points, and from there we can calculate what would be the normal direction of that specific point on the surface. So we have to evaluate our subdivided surfaces, and we can use a UV coordinate based on a multi-dimensional slider that you can actually find it here in the input. MD stands for multi-dimensional slider. And then I can just connect it to the point here. Once you have it connected to the point, then you check, oh, this is not actually the outcome that you expected. What we wanted is points on the center, which here 0.5, 0.5 actually represents the center of every subdivided surface. So this is how it's I'm going to explain. You have to reparameterize the surface input. That's because you are defining a parameter for the surface within 0 to 1. So it's like 0, 0 is one corner of your surface, and then 1 and 1 are the other corner. So we want to find out what is 0.5 and 0.5 on our surface. So for finding this location, we have to reparameterize the surface. And what does reparameterize do is that it creates a 0 to 1 domain for our surfaces. So therefore then this finds a meaning, 0 to 1. This is how we can evaluate our surface within 0 to 1 parameters. This also works the same for curves. If you, for example, want to evaluate a specific point on a curve, you have to reparameterize it. So now we have the location of these points, which are the center of our subdivided surfaces. If I just want to actually only visualize the points, I can just take that as a data. Then at that specific point, we have a normal direction, we have a U direction, V direction, and a frame. So this is very handy. So now we actually have all those frames that we can use later in the process. So for now, we are going to use the points excuse me, sorry, the normals to offset our polylines um, in the direction of the normal. So if I want to move them, basically, offsetting means here, I mean moving out. I move my curves with this specific normal direction. But then, of course, I want my curves to be, well, the data structure here is a separated branches of data, and therefore here I also have to end up with, instead of having one branch with including all the data, I have to also graft it into separated branches of data that each include one item in. Basically, I have to graft it, and then that way I can have 225 curves that are moved along the normal. I can use amplitude to manipulate the length of my vectors so that I can have a factor for extrusion. For example, I want to be like from 0.005 to 10, any number you want. And then you give that as a motion vector. So then I can, with the slider, actually say, I want to stop here or wherever. But then it seems that a lot of these are kind of colliding or intersecting with each other, and that's not what we want. So in order to be able to make a clean loft, maybe we have to scale them down. And you want to know when you want to scale some object or a geometry down, then you need to have a reference point and then the scale factor and your geometry as an input. So if I want to scale it down, I give the geometry here, and what is that this plane here represent is that reference point that I mentioned. So I want to make sure that that reference point is somewhere exactly also the center point of these polylines that are moved. So I think the best way that we can use that is if we just move the points again, also grafting it to keep the same. Yeah, so we can also move the points with the same motion vector so that we have the center points of our polylines as well. And then I'll use those as the planes here, plane input. And then what would be my scaling factor is the numbers that I would give here, for example. Well, it should be, if you want to scale it down, it should be something smaller than 1. So this means I want it by half, or I want it by 0.9, or 0.1, or etc. If you add a number higher than 1, you'll end up actually increasing the size, scaling it up. So I want to check if I want to, for example, like scale down these separately. Well, in this case, I would recommend to have same number for 3 of them because we want to end up having the same sort of orientation. And then I can preview off the moved curve, so, and also the points, so that you will see that all the moved or offsetted curves, polylines, are already scaled down by half. And here I want to point out that these polylines are the second polylines that we want to use, so that we want to actually make a loft between them. So if I just use loft, I want my first set of lines, and the second. So I have to make a list in which the first lines sit in the first stream, and the second ones are in the second stream. I'm using a component called weave. Weave is a component that mixes, it creates a list out of a mix of 2 stream data, or 3 or more, or whatever. Like you can actually increase or decrease these inputs. And you give it a pattern. Here, what is the pattern is 0, 1. So it means take the first item from 0, 1, from the stream 0 and put it next to the first item of the stream 1. And then the result would be the same number of branches, 225 branches, within which I have 2 items. One item from the 0 stream and the other item from the 1 stream. So this is how we make sure that the first polyline gets lofted with the first with the same second polyline accordingly in correlation. And if I now use Loft, you'll see that I sort of created that extrusion effect. And I can now change the, for example, the dimension of the scaling factor here and close these down or open them up. It helps maybe better if I now go, on preview. But this is only extrusion based on one factor, which is just here. Where was it? Sorry, here. This factor is the only parameter that gives us the extrusion. If I just decrease this, all of it will be shrunk down to 0.9, or if I increase it, it will just be more extruded up to whatever number it is. But I want to use Attractor to change a variety of inputs for my extrusion based on the distance. Based on the distance to whatever geometry that I'm defining as an attractor. Here I want to use a curve as an attractor, so I can argue in Grasshopper that, hey, wherever it's closest to this curve, extrude less, for example, and wherever it's further from the curve, you can extrude more. And how do we do that? Well, this is the basic lofting that we did, the extrusion we did, but now I can add more variation in the process. So first I want to define this curve as my attractor. So I'll just type curve because I want to assign it to Rhino. And well, I can preview, I can hide it from the viewport. And I want to find the distance of this curve to every single point, center point on this subdivided surfaces. One smart way, one of the best ways to do it is to actually find the closest points to the curve. And the points that we're going to search from are the same points as the center points. So I'll just type closest points. And one of the components here showing up is curve closest points. That's what we want to use. That way, basically, we can find what are the curve's closest points and also extract the distance from it. The other way is to just say, I want to, for example, divide my curve into points again, also into a, for example, fairly high amount of points, like 200 or something, and measure separately the distance between these points and the ones on the surface. Well, both are the same, but I would really prefer the other one, closest points, and that's also a new component that you guys can learn. So I assign here the curve, and then I have to find out my points here. And if I click here, you will see a set of points here, of course. These are if you want to project with the shortest path, closest path on the curve from the points. This would be the locations that they will be projected on the curve. But that's not what we want. What we want is the distance. So we have a set of values here that we can make a domain from. And that's the domain that we want to use to remap in order to create our attractor. This is based on the tutorials that you guys actually have seen before. So I can preview this off as well. And the things that I'm very first interested to get out of this distance is to find out actually what are the bounds, like what is the minimum distance and what is the maximum distance. This is the source domain. These are the source values. This is the source domain. And later I have to create another domain which will be the target domain. If I just type construct domain, and I have to define two other values. For example, I want to say, hey, extrude them by 8 if they are further from the point, and then extrude them by minimum 0.06, for example, if they're closest. So then I'm redefining this domain into a target domain, right? That's what I want to do. It starts from 8 to 0.06, whereas the other one starts from 8.3 to 20 point something. And then I have to remap these domains. The values are the distances, the source domain is the bounds, and then this is the target, and then I have the mapped numbers that here I want to use as the moving factor, the amplitude input. Instead of number 4.99 or 5 here, I want to use this list of numbers, 225 numbers, corresponding to the distance of the curve to the points in order to manipulate the height of the extrusions. So if I just use that, yeah, I also have to make sure that this list data structures are also compatible. Otherwise, I'll run into issues like this. So I have to graft the mapped output. I fixed the issue by grafting it, the outcome of the remapped numbers, so that it is compatible with the data structure of the other inputs, the vector inputs. And then here is the resulted geometry. If I check it out now, you would see the further you are from the point, the lower the extrusion is. And the closer you are, the higher the extrusion value is. So if I actually also just try to, again, get my curve back on the Rhino and try to change a little the inputs and play with the form of the curve, then you see, like, by changing that, I'm also affecting the distance of my curve to the surface, and then as a result, the difference in the extrusion heights. But I can also change the input values here as well. So for example, the closer you are to the curve, you would get smaller extrusions, whereas the further you are, you get more. I can, for example, work with that. I can work with the other option. And maybe number 8 is too big, and I'll just put it like a 4. So this is more of a pretty result to me. And so this is the attractor curve that I've made, actually, and these remapped numbers are the ones that I could use for moving for the extrusion factor. But how about, actually, guys, thinking about, like, now I want to use the same tactic for affecting the scaling factor. So it's basically using the curve again as a attractor, but then this time manipulating the sizes of the openings. So then I just have to define a new target domain, which will be definitely before under number 1. It should be smaller than number 1, so that it will be scaled down. So I can delete this one, but instead I go for 0.8 as the maximum, for example. 0.8 will be the maximum size of these extruded polylines, and 0.06 will be the minimum. And now if I give that as a target and also use this input, then I'm expecting to see that the openings are also affected by that. But then I'll just disable the component to save time for calculation every time that I add any input. And then in the end I can enable it back. And then here it is. This is the surface that is affected by my attractor curve in terms of openings and also the extrusion heights. And the more this curve is closed to the surface, you will see that the more openings, the more open the modules are, or vice versa. The further it is, the closer they come. So that's it, guys. This was basically the assignment. It's pretty easy. It's about like not even half an hour. And I also made it for you clean, neatly done with explanations, but then wires are disconnected. So this will be your job, your assignment, your task to sit down and after this video, watching this video, go through step by step and understanding what we're doing here. We're having a surface, subdividing it, extracting the edges, and trying to find out how to move those edges outwards based on the normal direction of the subdivided surfaces. And then we want to use a tractor curve to actually have a control over the amount of extrusion based on the distance factor. And at the same time, you can also change the openings of these curves, extruded modules, with the same principle of using the attractor curve. And yeah, hopefully this has been helpful, and then you guys can finish your assignments and upload it also on the wiki page after you're done. Thank you.